All right, the next thing we want to look at is implicit differentiation. So you might wonder, what is implicit differentiation? Implicit differentiation is when we're going to be differentiating. We cannot differentiate a function in terms of a variable explicitly. What do I mean by explicitly? Consider these two examples. So to find the differential of 3x squared with respect to x, we can do that because when we differentiate 3x squared with respect to x, we're just going to get 6x. Now look at this question right here. How would you find d by dx of 3y squared? Now there's no way on God's earth that we can differentiate y in terms of x because there's no x right here, right? So because we cannot do this, what we're then going to have to do is use what is known as implicit differentiation to do this. So now think of 3y squared as some letter a, right? And so think of it as a, and so in reality what we're trying to find is dA by dx. Just think of 3y squared as a, right? Just think of all of this as a. So dA by dx, well, from chain rule, we know that dA by dx would be equal to dA by something times something by dx. That's what we know. Now a is written in terms of y, and so we can then say that dA by dy times dy by dx will give us dA by dx. Can we agree? Because clearly right here, the dy's will cancel, or they would appear to cancel. And so we can differentiate a with respect to x by finding dA by dy and then multiplying the result by dy by dx. And so d by dx of 3y squared would be equal to, we would differentiate 3y squared with respect to y. Differentiating with respect to y, what we get is 6y times, after we differentiate 3y squared with respect to y, we get 6y times dy by dx. Times dy by dx. And so what we end up getting is that d by dx of 3y squared is 6y dy by dx. 6y dy by dx. So that's d by dx of 3y squared. It's going to be 6y dy by dx, right? That's d by dx of 3y squared. 6y times dy by dx. Now let's look at it in an example. Like, how are we going to use this in an actual example? So in an example, for example, let's say it's find dy by dx for the following. So x squared plus y squared is equal to 25. So to differentiate this function, x squared plus y squared is equal to 25, right? What we would do right here is we're then going to say, okay, we can differentiate the x part with respect to x, but we cannot differentiate y squared with respect to x. So we're going to have to use implicit. So the first step is to write d by dx. We're going to differentiate the entire equation with respect to x. So we're finding d by dx of x squared plus y squared equal to 25. So that's step one. Step one. Now step two is we're going to differentiate it now with respect to x. So the differential of x squared, as we know it, that is 2x, plus the differential of y squared. Now we cannot differentiate y with respect to x. So if we think of y squared as a, it becomes dA by dy. And when we differentiate y squared with respect to y, we would get 2y, but then we multiply it by dy by dx. That's implicit differentiation. So that part becomes dy by dx. Then that is equal to, now when we differentiate the number 25, that's a constant, and so we just get 0. So to find dy by dx, the only thing we would then do is we just need to transpose and make dy by dx the subject. So if we were to transpose it, we would see that dy by dx, that is going to just be equal to, we can bring over the 2x to get negative 2x, and then that is going to be divided by, what is that, 2y, and so what we're getting is that dy by dx is negative x over y. dy by dx is negative x over y. Alright, now that's using implicit. Now we could have, of course, differentiated this function normally by writing y in terms of x. So I'm just going to do it right here. Now imagine, so we had x squared plus y squared is 25, right? And so what we could have done is, we could have said, all right, y squared will go equal 25 minus x squared, right? So y squared is 25 minus x squared. So we have a pre and state, so now boom. So we're going to take the square root now and say y is equal to 25 minus x squared, and then we take the square root of that, right? So y is equal to 25 minus x squared, we take the square root of that. Now we are able to differentiate this normally. We would be able to find dy by dx for this normally. So we could then find dy by dx for this by doing this now. dy by dx is equal to, now remember, 25 minus x squared, right? 25 minus x squared, square rooted. The square root is really to the half power. Always remember that square root is really to the half power. So this is really 25 minus x squared to the half power. That's what we really have, right? And so we could then differentiate this by carry down the power, so we get half, subtract 1 from the power, so we get 25 minus x squared, and then we subtract 1 from the power, so it becomes minus half times the differential inside the bracket, and the differential of minus x squared is negative 2x. Now pre this now, minus 2x times a half, so minus 2x times a half, that part there, make it work out to be minus 2x over 2, which is just minus x. And then whenever you have something in the numerator, which is raised to a negative power, it can become 1 over this thing, and put it in the denominator then. So that part becomes 25 minus x squared. 25 minus x squared square rooted. Now 25 minus x squared square rooted, we said that right here, that is y. And so dy by dx works out to be minus x over y. And so the question you might ask is, why then bother use implicit differentiation when we could just do this? Now, if every equation we were going to make y the subject in terms of x, that would take forever. Like look on this now, y and y cubed, you're going to have to do some factorizing and trying to simplify to get y in terms of x to then find dy by dx. That would take long. And so a simple way of doing it is just differentiate y with respect to x by using implicit differentiation. And there are also cases where we cannot simplify this equation y in terms of x. And so in those cases, we have to do implicit differentiation. And so right here now, question 2, we have to do implicit differentiation because there's no way, or it's going to be very difficult to write y strictly in terms of x. All right, so let me get rid of this part right here. This was just to prove that this answer is the same, all right, for implicit. But we won't be doing it this way, making y no subject. That would take forever. All right, now let's look at example 2. So for example 2, what we're doing is xy plus x squared plus y cubed is equal to 7. Now to differentiate xy, this is a product. So this is your u and this is your v. So what are we going to do? We're going to differentiate it using product rule. So the first step is to find d by dx of both sides. So d by dx, both sides. So we need to differentiate both sides first. So we're finding d by dx of xy plus x squared plus y cubed equals 7. So we'll find dy by dx of both sides first. Now, read this now. When you differentiate xy using product rule, it's going to be keep the first times the derivative of the second. The derivative of y is dy by dx. Just for simplicity, I'm going to write y prime. Y prime and dy by dx is the same thing. Plus keep the second, which is y, times the derivative of the first, which is 1. Plus, when you differentiate x squared, we're getting 2x. And then, when we differentiate y cubed, we have to differentiate y implicitly. So we bring down the power to get 3y squared, but then we have to times it by dy dx, which is y prime. And that's equal to 0. Now the next step to do is to make y prime the subject. To make y prime the subject, we have xy prime right here and 3y squared y prime. So we can group all the y primes on one side. So we have xy prime plus 3y squared y prime. And that is equal to, we bring over the minus y and bring over 2x, so it becomes minus y minus 2x. So now right here, we can factorize out y prime. So we can factorize out y prime, and we're left back with x plus 3y squared. So y prime times x plus 3y squared is equal to negative y minus 2x. All right. Now let's finish it off in a small space right here. We can finish it off in a small space right here. Right? So look at this now, pre. So if we were to divide through by x plus y squared on both sides, what we will end up getting is that y prime is equal to minus y minus 2x divided by x plus 3y squared. And that would be dy by dx. And so y prime, which is dy by dx, is equal to, so all I'm doing is changing y prime to dy dx. So dy by dx is minus y minus 2x over x plus 3y squared. And that would be dy by dx. Now this example right here seems a little more complicated, right? It looks a lot more complicated. So let's debunk this question. Let's get rid of it. So we need to find dy by dx for this third one. So to find dy by dx, again, we have to use product rule. So step 1, we have to write that we need to find d by dx of this entire thing right here, which is x squared y plus, now look how I'm going to break up e to the x plus y. By laws of indices from primary school or from grade 9 or grade 10, we learned that e to the x plus y can be written as e to the x times e to the y, right? And that is equal to, so e to the x times e to the y, and it's equal to 2x. Now let's differentiate this now. So now when we're differentiating x squared y, right, we're going to use product rule again, and product rule tells us that we keep the first, which is x squared, then we differentiate the second. Differentiating the second is y prime, plus we keep the second, which is y, then we differentiate the first, and when we differentiate x squared, we get 2x. Plus, we're going to have to use product rule again, and so we keep the first, e to the x, times the differential of the second. Now when we differentiate e to the y, with respect to y, we get e to the y. But then we're going to have to times it by dy by dx, which is y prime. Plus, keep the second now, e to the y, times the differential of the first. Differentiating e to the x is just e to the x, so we get times e to the x. That's equal to, when you differentiate 2x, we're getting 2. And so now, the second step is to make y prime the subject. So anything with y prime, we'll keep it on the left. Everything else we bring to the right. And so what we're getting clearly then is that x squared y prime, x squared y prime, plus x squared y prime, plus right here becomes e to the x plus y times y prime. That's going to be equal to 2 minus 2xy and then we need to subtract again e to the x plus y. Alright, now from these two we can factor out y prime, and we factor out y prime and we're left back with x squared plus e to the x plus y, and that is equal to 2 minus 2xy minus e to the x plus y. And so now we just need to go ahead and find dy by dx by dividing both sides by x squared plus e to the x plus y. And so what we're getting then is dy by dx is going to be equal to, we get 2 minus 2xy minus e to the x plus y, and that's being divided by x squared plus e to the x plus y. And that's dy by dx. Easy, soft. And this is how we apply implicit differentiation to find dy by dx of some functions that are given, or the equations of curves that are given. Alright? Alright, so we're back to differentiating logarithms now, but now we're differentiating y equal to a constant raised to the power of x. Well, some might say it's exponential, but I like to say differentiating logs because we're going to apply some logarithms to it. So remember when you're solving log equations from when you were doing CSEC math, CSEC odd math, you'd have learned that whenever the unknown is in the power, you take the log of both sides. Whenever the unknown is in the power, we take the log of both sides. And so what we get is, the log that we're going to take is the natural log, since we know how to differentiate the natural log. So what we get is ln y is equal to ln a to the power x. Now by rules of logarithm, we can bring down this to become x ln a. Right? We can bring down the power by laws of logarithm. Now, to differentiate ln y, we can differentiate ln y implicitly by differentiating ln y with respect to y first. When we differentiate ln y, we get 1 over y, then we multiply it by dy dx. And then that's going to be equal to differentiating x ln a. Think of ln a as a constant. ln a is a constant. K times x. When you differentiate k times x, we just get k. And so differentiating x ln a just leaves ln a. So if we multiply this equation now through by y, we end up see that dy by dx is going to be equal to y ln a. But then what is y? Y from the question is a to the power x. And so y is a to the power x. And so dy by dx is a to the power x times ln a. That is dy by dx. Dy by dx, when you're differentiating a to the x, is a to the power x times ln a. Nice. Now let's look at these two examples right here. So part 1, y is equal to 5 to the x. So if y is equal to 5 to the x, then dy by dx, or y prime, is equal to a to the x, which is 5 to the x, times ln a. And ln a, in this case, a is 5, so it's times ln 5. All right. Now question 2 is a little bit different. Question 2, it asks y is equal to 3 to the power 2x, right? Y is equal to 3 to the power 2x. So if you were to observe this one where y is equal to 3 to the power 2x, y is equal to 3 to the power 2x, because x is being multiplied by 2 is a little different. So if you were to take the natural log of both sides, you'd see that ln y is equal to 2x ln 3, right? Or ln 3 to the 2x, but then we can bring down the 2x same way, right? So I'm just doing it in this 2-step in one. So to differentiate ln y, we get 1 over y dy dx. And 1 over y dy by dx is going to be equal to what? 2 ln 3. 2 ln 3. But then what is 2 ln 3? 2 ln 3 is ln 3 squared, which is ln 9. Right? And so let's finish this question in this box right here. So what we get then is 1 over y dy by dx. 1 over y dy by dx is equal to ln 9. That's equal to ln 9. And so we can multiply through by y to get that dy by dx is equal to, dy by dx is equal to y ln x. Y ln 9 rather, not x, y ln 9. But what was y? Y was 3 to the 2x. So it becomes 3 to the 2x, 3 to the 2x times ln 9. 3 to the 2x times ln 9. Easy question. And that's how we differentiate a to the power x.